Every computer uses binary instead of the decimal system we're used to because electronically, comparisons are made based on the state of a signal. And that state is either on if electricity is present, or off if electricity is absent. These states are also called true and false, high and low, or 1 and 0. The way these states are measured and compared is with the revolutionary transistor, which we talk about in a separate video. Today, however, I want to talk about how easy it is to use the binary system. When first learning computer science and number systems, it's easy to believe that this binary system that computers use is some unique code that has no relationship to the decimal system we use as humans. In reality, binary is exactly the same type of system as decimal. The only difference is a single parameter known as the base, or radix. Decimal is a base 10 number system, meaning there are 10 symbols used to represent numbers. When we count in decimal, we start with 0 and count up through 9, but we run out of symbols to represent numbers higher than 9. So we start using 2 symbols. We increment the digit to the left of 9 and reset the 9 back to a 0. This left digit in a spot known as the tens place only increments when we run out of digits in the place to the right, known as the ones place. And this pattern continues on to infinity. This system is exactly the same with binary. We increment the ones place until we run out of digits, which is very quickly because there are only 2 digits in binary, 0 and 1. We then increment the next place over and reset the ones place. Notice that the name of the next place over is not called the tens place because we have not yet reached 10. It took 2 increments to reach this place, and therefore this is the twos place. We then have the fours place, the eights place, and so on. Each place has twice the value of the previous place. This also means that the values of these places are powers of the base of the number system. So 1 is 2 to the 0, 2 is 2 to the 1, 4 is 2 to the 2, 8 is 2 to the 3, and so on. In decimal, this system remains true, just with bases of 10, of course. This binary system is how everything is represented for computers. The position and color of each individual pixel on your screen right now is represented by a combination of ones and zeros. And how we get things other than numbers to work in binary is through certain codes, like ASCII, which we can discuss another time, but there are more interesting things to unpack with just numbers for now. For example, negative numbers. When simply notating numbers, we use a dash in front of the number to represent its negativity. But computers, of course, only have room for ones and zeros, so we simply use a bit at the beginning of each number to represent its negativity. If that bit is 0, the number is positive, and if it's 1, the number is negative. Now, unfortunately, we cannot just take the positive version of a number and flip the negativity bit to get the negative version of that number. And the reason for this takes a bit of explanation. Let's say we have positive 3, which for a 4-bit number is 0011. And if you don't quite understand why, pause and think about what each 1 represents in binary for this case. So positive 3 is 0011, and to get negative 3 according to the system I just described, we simply invert the first bit to get 1011. But what happens if we add these two numbers together? I'll explain addition in more depth in another video, but we can see here that we don't get 0, which is what we would expect for 3 plus negative 3. Oh, if only that just worked. Instead of only inverting the first bit, we invert every bit. This system makes more sense, so engineers decided to give it a name. It's called ones complement. For positive 3, or 0011, the inversion of every bit results in 1100. But again, we can't quite call this bit negative 3, because if we add positive 3 and this number, we get 4 ones instead of the desired 4 zeros. Now, ones complement has a negative version of every number, and this includes 0. So invert 4 zeros and we get 4 ones. There you go, negative 0. This addition of 3 and the ones complement version of negative 3 resulted in this negative 0. And this may be practical for a small amount of applications, but computers would think the negative 0 is different than actual 0 because the bits are different, so they take one more step after inverting every bit to get true 0. If we first negate every bit as we did before, but then add 1 to the number, we get what is called the twos complement of that number. This is officially -3 to a computer. When we add +3 in this version of -3, we finally get 0. Notice that there's a carry bit all the way on the left that is ignored when we add a positive and negative number together. This is completely legal in 2's complement and should be ignored because we can only have a 4-bit answer anyway. That bit is there because we simply maximize the 4 bits we have, but if we increment one more time, we get 16, which we cannot store in 4 bits. So by design, a carry bit is dropped, and we wrap around back to 0. Let's take another look at this negative bit. Good computer scientists might call this a negative bit, but great computer scientists might call this the -8's place. To see why, let's take another look at -3. The 1's, 4's, and -8's place are true, so we add 1 plus 4 plus -8, which results in the expected -3. This is how every number works, and every addition for each combination of numbers also works, except in the event of an overflow. And an overflow is when the result of an operation is too large to fit in the number of bits we are working with. Note that this negativity bit is only called the -8's place in a 4-bit number, because 2 to the 3 is 8. In an 8-bit number, this would be 2 to the 7, which is 128. So we might call the leftmost bit the -128's place in an 8-bit number. In the next video, we'll learn about transistors so we can compare numbers. And if you're interested in performing operations like addition, that'll be covered in the next several videos, so stay tuned.